Good morning, everyone, and welcome to today's presentation. I'm Dr. S.K. Singh, holding a PhD, and I'm excited to share with you some insights about the qualification of BOD Incubator. Today, we'll explore the key aspects that define its standards and capabilities. Over the next few minutes, I'll walk you through the essential features, the importance of quality benchmarks, and how this incubator can support innovative ventures. Let's get started. Let's start by understanding what a BOD incubator actually is. It's an instrument designed to maintain a controlled temperature environment, which is essential for conducting BOD tests and cultivating microbial cultures. These incubators are widely used in environmental laboratories, pharmaceutical quality control, research and development, and academic settings. The key point here is that they provide a stable and reliable environment, ensuring that incubation conditions remain consistent. This consistency is crucial, especially when performing stability tests or other experiments where precise temperature control directly impacts the accuracy of your results. Now, moving on to why qualification of these incubators really matters. From a regulatory perspective, it's about making sure the equipment performs exactly as it's supposed to. Compliance standards like GMP and ISO 17025 require that we verify and document that our equipment is functioning correctly. This helps prevent data variability, which can lead to incorrect conclusions or regulatory issues. Plus, during audits or inspections, having solid qualification evidence shows that we're committed to quality and compliance. Ultimately, proper qualification supports the integrity of your testing process and ensures reliable, trustworthy results. Let's take a closer look at the qualification lifecycle. This slide outlines the key phases involved in qualifying a system or equipment. First, we have the IQ, or installation qualification. This step verifies that the equipment has been installed correctly according to specifications. It's about making sure everything is in the right place and properly configured. Next is the OQ, or operational qualification. Here, we test the equipment to confirm it operates as intended under normal conditions. It's about validating that all functions perform reliably and consistently. Finally, we move to PQ, or performance qualification. This phase demonstrates that the equipment can perform its intended tasks effectively in real-world production scenarios. What's really important to understand is the sequential order of these phases. Each step builds on the previous one, ensuring that we have documented proof of capability before actually using the equipment in production. This structured approach helps us maintain quality, compliance, and confidence in our processes. It's a critical part of the overall qualification strategy that supports manufacturing excellence. All right, let's talk about IQ, or installation qualification. The main goal here is to ensure that the unit we received actually matches what we specified. For example, if we needed a temperature range, we want to double-check that the unit operates within that range. It's also critical to verify that the installation follows the manufacturer's instructions closely. Proper installation is key to making sure everything works smoothly and reliably. Another important aspect is confirming that all utilities, such as power, exhaust systems, and software connections, are correctly connected and functioning properly. This step helps prevent future issues and ensures the system is ready for operation. Overall, IQ is about making sure that everything is in place, correctly configured, and ready to support the next phases of our project. It's a foundational step to ensure quality and compliance from the very start. Now, let's talk about operational qualification, or OQ for short. The main goal here is to verify that the BOD incubator functions properly across its entire operational range. This means we need to make sure it performs reliably under different conditions. Typically, we conduct several key tests. First, temperature uniformity. That's checked at 5 points, the 4 corners and the center of the chamber. This helps us ensure that the temperature is evenly distributed. Next, we look at temperature stability over time, which might mean monitoring the incubator for 24 to 72 hours to see if the temperature remains consistent. And finally, we check the alarm and control systems to make sure they activate correctly and function as intended. Now, regarding acceptance criteria, or the standards the incubator needs to meet, let's look at an example. Suppose our set point is 20 degrees Celsius. We want the temperature to stay within a tolerance of plus or minus 2 degrees across the entire chamber. That means the temperature should stay between 18 and 22 degrees. Additionally, uniformity should be within a maximum of 2 degrees difference overall, ensuring no significant hot or cold spots. These criteria are critical because they help us confirm that the incubator can maintain a stable, uniform environment, which is essential for reliable biological experiments. Connecting this to our overall quality assurance, performing these tests and meeting these criteria ensures that the incubator is operating correctly, providing confidence in the consistency and accuracy of our results. Now, let's take a closer look at an example of OQ data mapping, specifically focusing on temperature mapping. This is a practical illustration that helps us understand how data points are mapped and organized within a temperature monitoring system. By visualizing this example, we can see how each temperature reading corresponds to specific locations and times, which is crucial for maintaining quality and compliance. It's important to grasp this concept because accurate mapping ensures we can identify temperature variations quickly and respond appropriately. This example ties into the overall theme of the presentation, emphasizing the importance of precise data management in quality control processes. Remember, clear and accurate data mapping is key to effective monitoring and regulatory adherence. Let's talk about the purpose of performance qualification, or PQ. The main goal here is to demonstrate that the incubator performs consistently under typical use conditions. This step is crucial to ensure reliability and stability in our processes. Now, when it comes to the test plan, we simulate real-world scenarios by loading samples that replicate our usual quality control tests. We then run these tests 3 times in a row to verify consistency across multiple runs. During these runs, we assess several key parameters. Temperature is obviously critical, but we also monitor data logging to ensure accurate recording of conditions. If humidity is relevant to your process, that's checked as well. Overall, PQ helps us confirm that the incubator maintains the right environment reliably, which supports the integrity of our QC results and ensures compliance with quality standards. Let's take a look at this example of PQ results. Here, we have hypothetical data from 3 different runs. The idea is to see how the results can vary across multiple attempts. It's important to understand that these numbers give us insight into the consistency and reliability of the process we're analyzing. By examining multiple runs, we can identify patterns or anomalies that might not be obvious from a single data point. This approach helps us ensure that our conclusions are robust and not just due to chance. Ultimately, this example highlights how key performance metrics can be tracked over several runs to inform better decision-making and process improvements. Let's take a closer look at the OQ protocol outline. First, we focus on the purpose and test plan, which sets the foundation for what we're aiming to verify and how we'll approach it. Next, we have the temperature mapping method, where we detail how temperature data will be collected and analyzed to ensure consistency across the environment. Calibration of loggers is also crucial, as it guarantees our measurement devices are accurate and reliable throughout the testing process. We then move to the data recording schedule, outlining when and how often data should be captured to maintain a comprehensive record. Acceptance criteria come next, defining the specific thresholds our results must meet to be considered successful. After that, we review results and deviations, which involve analyzing the data, noting any anomalies, and understanding their impact. Switching gears to the IQ protocol outline, we start with the objective and scope, clarifying what the verification aims to achieve and its boundaries. Equipment details are included to specify the devices involved, ensuring traceability and compliance. Installation verification steps are critical. They confirm that equipment is installed correctly and functioning as intended. Again, we specify acceptance criteria to determine if the installation meets the necessary standards. Finally, results and signatures are documented to formally validate the verification process and assign accountability. As an example, the IQ protocol outline provides a clear template for structuring these verification activities, ensuring all key points are addressed systematically. Overall, these outlines help us maintain consistency, thoroughness, and quality across our validation efforts. All right, let's look at an example calculation for uniformity. The key idea here is to measure how consistent the temperature is across a given area or sample. We do this by taking the maximum temperature and subtracting the minimum temperature. That difference gives us the uniformity. For instance, suppose the maximum temperature recorded is 20.3 degrees Celsius, and the minimum is 19.8 degrees Celsius. When we subtract the two, we get a uniformity of 0.5 degrees Celsius. Since our acceptance criterion is that this difference should be less than or equal to plus or minus 2 degrees Celsius, and in this case, it's just 0.5, which is well within limits. Therefore, we can say this sample passes the uniformity test. The main takeaway here is understanding how small the temperature variation needs to be to meet quality standards, and this simple calculation helps us determine that quickly and effectively. Let's talk about some best practices to ensure a successful validation process. First, pre-qualifying calibration devices is crucial. This means verifying that our calibration tools are accurate and reliable before using them in any testing. It helps prevent errors down the line. Next, adopting risk-based acceptance criteria allows us to focus on the most critical aspects of our validation. By assessing risks early, we can prioritize testing efforts where they matter most and make informed decisions about acceptance standards. Another key point is conducting cross-team reviews, especially involving QA and engineering. Collaboration here ensures that all perspectives are considered, potential issues are caught early, and we maintain high standards throughout the process. Now, moving on to common pitfalls to avoid. One of the biggest mistakes is skipping load testing during performance qualification. This can lead to overlooking how the system behaves under real-world conditions, which is risky. Poor documentation is another pitfall. Without thorough records, it's hard to demonstrate compliance or troubleshoot issues effectively later on. Proper documentation is the backbone of a robust validation. Finally, neglecting to calibrate sensors can seriously compromise the accuracy of your data. Regular calibration ensures that all measurements are precise, which is essential for reliable validation results. Overall, by following these best practices and avoiding common pitfalls, we can make our validation process more effective, reliable, and compliant with regulatory standards. Let's wrap up with some key takeaways. First, qualification is crucial because it ensures both reliability and compliance in our processes. Without proper qualification, we can't be confident that our systems are performing as expected or meeting regulatory standards. Next, it's important to remember that a structured approach, starting with installation qualification, then operational qualification, and finally performance qualification, is essential, especially in regulated labs. This step-by-step process helps us validate that everything works correctly and consistently. Another point to keep in mind is the importance of good documentation. Clear, thorough records, along with relevant examples, really strengthen our audit readiness and demonstrate that we follow best practices. Lastly, I recommend using standard templates and setting clear acceptance criteria. These tools help ensure consistency across projects and make it easier to evaluate whether systems are ready for use. Overall, these points tie back to our overall goal: maintaining high quality, compliance, and readiness in our laboratory operations. For further support, please don't hesitate to reach out. We're here to help with any questions or additional information you might need. Feel free to contact us anytime. And with that, I want to sincerely thank you for your time and attention today. Your engagement is truly appreciated, and I hope you found this presentation valuable. Remember, we're always available to support you as you move forward. Thank you again.